actually first speaker of the ICAM Summer School, Professor Tim Sluckin, and he will give us a lecture on history of liquid crystals, right? So we have mostly young people in the audience, and we will learn a lot about what happened decades and hundreds or more years ago in history of liquid crystal that is important. So let us switch the presentation. Yeah.
Yes, it's great.
Okay. Let's see, where is yours?
It's on the desktop.
Okay. We may need some help.
Steve!
Let's see, which one is this? This one?
It's probably the PDF.
PDF, okay. All right.
All right.
So let us switch the mics.
Okay, good.
And do you need this too?
Hang on just a moment. I can put my weapon away.
We'll keep it on.
Okay. Good. Okay, I'm Tim Sluckin. I'm from the University of Southampton, and my field was originally the theoretical physics, applied mathematics of liquid crystals, but in the last 15 years or so, I have been interested in the history of liquid crystals. And so what I'm going to do today is to give you some pictures about episodes. History of science is a serious subject, but of course, in the nature of serious subjects, you can find some things that are more serious and some things that are less serious. And the first thing that I need to ask you is, what is this? Professor Cameron, what is this? That's an adjective, Professor, not a noun. This thing, give me the name of this thing here. He's failed immediately. Do something right. Yes, sir. No, wrong. It's Professor Alexander.
Sphere.
A sphere. Good, all right. They're jokers. It's a cricket ball. Thank you very much. It's a cricket ball. And I can see around that there are... You, sir. Sorry, what's your name? Yes.
Rishan.
And are you a cricket player?
I do play.
You do play, okay. So later on in this lecture, I will need a team of cricket players. So all of those that are experienced in playing cricket, there can't be somebody here who does not play cricket.
And proudly.
Let me just look to see a possible non-cricket player. You, madam, are you a cricket player? Yes, you. The lady with a blue... You've never played cricket? That's a terrible thing. It's a terrible thing. It's a terrible thing. Later on, we will need to have... I'm going to volunteer some of you to play cricket. Okay, now, which direction do I point this in? No? Yay! Okay. All right, as a theoretician, of course, I don't know how, I can't use pieces of electronic equipment, and that's why Professor Smalyuk will be my assistant here and help me if things go wrong. And if, on the other hand, there is any misbehavior, I have a special kind of liquid crystal. Here you can see this kind of liquid crystal. It changes the ordering properties of the liquid crystal in a quite unpleasant kind of way. And so I just want to warn you that you may be aligned if there's any misbehavior. Okay, so I'm going to give you, how many people would pass an exam in liquid crystals? Nobody, typical. What are they doing here? Okay, so I'm going to talk just a little bit about liquid crystals. I'm going to talk something about history. I'm going to talk something about devices. And then there'll be just a little bit about what's going on in the field. There'll be a commercial at the end because our sponsors require a commercial. And after the sponsors have finished their commercial, there will be a panel at which Professor Lubensky will give us the... pardon? Oh, okay, not only Professor Lubensky and his assistant will give us some, give us the benefit of their wisdom. Okay, so this is the Isaac Newton Institute for Mathematical Sciences, and so we need an equation, and here is an equation, and that's that. Okay. Okay. So I knew you'd be keen on equations, and so I thought I'd give you an equation. There must be some math-type people here, and, you know, again, our sponsors require that we have to have an equation. Okay. So this is a story of some accidental and some deliberate discoveries, and a lot of it is to do with Germans, and a lot of the early history is to do with discoveries by Germans. Do we have any Germans in the house? Yay! Okay. So when we get to the good bits, you can stand and everybody can give you an... Okay, so I'm going to talk something about the personalities, a little bit about the physics, mainly physics, something about social history, and obviously, when it comes to history, you find two different historians. You know, if you go to a different course on the same stuff in a math department or a physics department, roughly speaking, you get the same stuff. And if you go to two courses on the same piece of history, well, historian A would fail historian B, and historian B would fail historian A. So that's the kind of area that we're going to be in. And occasionally, we're going to get a few test questions, and I have to tell you that with most of the test questions, there isn't going to be a right answer. Actually, oh, the commercial, the sponsor is me. Okay, that's fine. Okay, so just a brief summary of liquid crystals. Structurally intermediate between liquid and crystalline phases, except when they are not, because Professor Warner will be telling us when they're just ordinary solids. And they aren't crystals, and there are a whole set of liquid crystals, and in particular they flow in very peculiar ways. That's what we mean by non-Newtonian. Hang on. Which bit do I press to get it to point? Oh, there. Good. Okay, fine. Broken symmetries, in other words, some directions are special. You'll probably hear a lot about topological defects. They are optically birefringent, and that's, of course, the key to most of the devices. And, okay, not crystals, but liquids with some remnant of crystalline order, often made, as we know, from molecules, sometimes not as awkward as this, sometimes like this. And we have some other stuff down here as well. Optically anisotropic, produce brightly colored patterns in a polarizers, between cross polarizers known as textures. Lots of complicated phase diagrams, which thermodynamics people can get really excited. Two flavors, thermotropic, the thing changes when we change temperature. Lyotropic, when we change, usually when we have stuff that is dissolved in water, and we change the concentration in the water. And of course, we are going to see a lot about topological defects. Okay, so here's a picture. There is, oh dear, I'm no good at this. Oh, there we are. Okay, so, whoops! Oh no! All right, somebody help me here.
Use the stick.
Oh, no, but I need to go back. I need to go back. What do I? Oh, here we are. Oh, there we are. Okay, that's good. Thank you. Okay, so there. Oh, I'm not ambidextrous.
Other end. Other end. Yes.
Okay, so there is a nematic phase, no order, no positional order. Here's a right, but all lined up. Here's a smectic phase where we've ordered ourselves into layers. Right, here's a so-called cholesteric phase in which the molecules are sort of turning around. And this is a kind of model, courtesy of Professor Coles. And you can sort of see the spiral, the analogy between the excuse me, and the thing that's going on there. And finally, okay, there's the so-called smectic C phase. Once again, they're in layers, but instead of them layers being perpendicular, they're at a kind of angle. Okay, and here are some phase diagrams. Sorry? Oh dear. Thank you. Okay, thank you. Okay, so okay, so here are some phase diagrams, again, stuff that we're going to learn more about later, showing if you go at the top, they are the most disordered. At the bottom, the crystal is K because of our German friends who started the whole thing, and the K, apparently in German, crystal begins with a K. Of course, they've got it wrong, but what can you do? And in between, various kinds of other kinds
Microphone.
of... Have I done something to it?
Is it on?
Is it on?
In your pocket. On the top.
I need an assistant. Did I do something?
You have the power to turn the battery on. We'll bow down.
Okay, so again, stuff that we're going to learn about in the next couple of weeks. Gradually, as you go from the bottom to the top, you reduce the amount of order, and sometimes you tilt the molecules with respect to the layers. Okay, let me go back to the beginning of the liquid crystal story, or almost the beginning of the liquid crystal story. It occurred in, here we are, 1888. Right, when a fellow called Friedrich Reinitzer in Prague, about 1.5 years ago, I reported the results of some studies of cholesterol occurring in the root of the carrot. Everything, all of the device industry, everything, it all started with carrots. And it's interesting because he was a biochemist. He wasn't interested in screens. He was simply looking at the compounds. He wanted to know whether the whether the cholesterol in the carrots was the same as the cholesterol in the rabbits that ate the carrots. Anyway, so he did this, and he, whoops, there we are. Here's his experiment. He studied a derivative of the cholesterol benzoate. This is what the molecule looks like. Of course, they didn't know that nowadays. Here it is, it's some complicated formula. And the most interesting thing that he discovered was that the crystal melted to a liquid. I mean, we call it liquid crystal now, but it was just a cloudy fluid. There we are. It was a cloudy fluid, a little bit like this. But it was at 145.5 degrees centigrade. And then at a hotter temperature still, right, this cloudy fluid went clear. And he did various things. Of course, he was a biochemist. What could he do? He wrote to a crystallographer. He discovered that there were some colors close to the critical clearing point, and his crystallography colleague observed crystallites. And here's a picture. There is my Bunsen burner, because I'm an experimentalist, right? There's my Bunsen burner, and here are the colors that are observed at the clearing point. And you can see here it is a little bit cooler, where the top is still in the cleared state, the bottom is a cloudy state, and that's why we talk about the clearing point, the temperature at which you go from a liquid crystal to an isotropic fluid. Okay, so now I have a question. This is the bottle on the desk, and now, hang on, how do I do this? I press a button. Right? So now you have 4 choices. Right. This contains a sample of bull semen. Right. Actually, they went on a walk, these liquid crystal people. They went to Grantchester, and that's where they got it. Alternatively, it contains milk from the fridge upstairs with colored chocolate nanodroplets. It's a cholesteric liquid crystal with a formula too long to fit into the margin. We're in mathematics. Or white paint scooped up from my floor. Not It's all right. Just come. What did you want? All right. Vote now. All right. Vote now. Okay. Have I done this right? All right. Can I see what the result is?
Click again on AE.
Right. We're practicing. Huh? I don't know. It's yeah. Has everybody voted? Put your hands up if you haven't voted. Okay, we're going to see what the result is. Do I press this one?
Red button first.
Red.
Oh, okay. Thank you.
And then the second one.
Oh. Okay, so we were just about right. Okay, that's very good. Why is it question 5? Oh, well, never mind. All right. This is just a... Whoops. All right, now what do I do? Why is it not...
Click on the screen.
Do I have to click on something in order that... What do I have to click onto? Okay. Okay, so the kind of things that they were interested in as scientists were what was causing the peculiar double melting, right? What was causing the peculiar colors, right? Well, the obvious thing was, right, if you look carefully, you'll see some colors here. Obviously, there must be some pigment, and it's interesting, the paper just has a sort of little mention of this fellow who actually did the crystallography at the bottom, and it says, "Thank you, Dr. Lehmann, for some microscopy." And here's a copy of one of the letters. They had an enormously long correspondence, right? And Dr. Knoll in Karlsruhe has actually translated these squiggles apparently into German. So who would know? Okay, so this Lehmann is generally regarded as the founder of the liquid crystal field. It took him, he started his studies in 1889, and you can see that he talked about flowing crystals, he talked about slimy flowing crystals. Kristalliner Flüssigkeit was a crystalline liquid, and Tropfbar means drop forming. So it took quite a long time before the language sort of settled down. Here he is in his lab with his microscope, and the microscope was really important because it had a hot stage, and because it had a hot stage, all of this stuff was taking place at temperatures that are far higher than 150 degrees centigrade, and so you needed this hot stage. So right. So he really made the subject come alive. He used this polarizing microscope. I'm going to show the microscope in a minute. He applied it to Reinitzer's cholesterol benzoate. He identified birefringence and flow. So birefringence was the important thing. And previous to that, you never got a birefringent fluid. If you had something that was birefringent, it might be something like calcite, it could be a quartz, it could be a solid, and that was why it was some kind of crystal. And so here we had birefringence in a liquid, and that was the key that meant that it must be a liquid crystal. And there's a lot about how come something could be both liquid and crystal at the same time. And the important thing that we have to remember is that at that time, nobody had ever done an experiment that showed that crystals consisted of particles in lattices. Those experiments didn't come until 1912, 1913, X-ray crystallography. All of that was in the future. The lattices were simply a theory at that time. Here's a wonderful picture of the microscope, and he had a deal with Zeiss, actually, who were making these microscopes. And there he is looking, well, he was quite pleased with himself, actually. And here's his book, and you can see, right, you might see here, you think, is the book called Liquid Crystals? Right, you like to have a catchy title for a book, right? But no, right? And plastic of crystals in general, molecular, blah, 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 goes on forever, right? So, right, So this is the title page, right? And actually he was a really interesting guy. He almost won the Nobel Prize in 1913, but just failed outright. And here are some pictures that are taken from his from the book in 1904. And look at these beautiful colors. And the beautiful colors are things that he saw in the microscope, but of course they didn't have color photographs in those days. So he sat there. Well, actually, it was an important professor. He didn't sit there. It was his assistant who sat there, obviously, and colored it in very carefully. And so you got all of these beautiful pictures. And these beautiful pictures are things that that in fact we are investigating to this day, or various pretty kind of all sorts of configurations, liquid crystal configurations that are sitting inside these droplets. Okay, so the photographs were really in black and white. Okay, a couple of years later, after all of this, this fellow Gattermann actually synthesized a liquid crystal. So he's the very first one to synthesize a liquid crystal, and the thing that he synthesized was called para-azoxyanisole, and it went to a liquid crystal at 116 and to a proper liquid, to an ordinary liquid at 134, and this was the liquid crystal that they used to do their experiments on for many years. And actually he later became a famous organic chemist. He authored the premier textbook of the day, and a lot of people thought he was a kind of boring guy. You know, you can imagine physicists saying, well, you know, they make these things, these organic chemists, but they're pretty boring. And but what is interesting is that his work was being funded by a dye company. And they thought, oh, look at all these bright colors. The bright colors must be possible to use in dyes and colorings in clothes. So that's probably why they were funding the work. And here he is in his lab. And he died when he was only 60. And you can see there that there's a cigar in his mouth in the chemistry lab. And one can imagine, one can imagine that the health and safety people might feel just a little bit peeved about this kind of thing. But anyway, so there were, but the people in Bayer's dye works in Elderfeld were not worried about anything like that. It was only much later that the chickens or the cigar smoke came home to roost. Okay, so he was an imaginative kind of guy. I mean, he was the son of a baker, obviously must be an imaginative kind of guy. And the drops merged. This is reported in his paper. The drops merged, the patterns deformed very quickly, right? No one really understood. They saw these kind of lines of force. They called them Schliere, which means kind of stains, and that word remains in the liquid crystal vocabulary even now, the Schlieren texture. It comes from this. Well, maybe it comes from this, or maybe there was a fellow called Schlieren. Nobody really knows. But Gattermann, he had a vivid imagination.
Professor.
Yes?
Do you believe that the word Schlieren should be capitalized in papers or not?
It's an adjective.
I take questions after the lecture. Thank you. I have a nice weapon here. I don't interrupt your lectures. You don't interrupt mine, okay? But I may be able to use you for a cricket demonstration later on.
As the ball.
Okay, so here we are. After the drops amalgamate, the molecules reorient according to their mutual lines of force. I call this process copulation. Now, I should tell you that when we were translating for our book, this comes from a translation of papers for our book, my chemistry colleague who was busily translating all of this, and he completely missed this, completely missed. I said, this is the only place until about, two or 3 years ago that sex enters liquid crystals, and you've missed it out. So anyway, what's the interesting thing? If the merging drops are very small, then the copulation proceeds so quickly. That's the thing, we wouldn't like that, would we? A copulation that proceeded quickly, and so it can't be separated from the amalgam. Okay, here are some textures, right? Different kinds of textures, right? Of course, colleagues can interpret these textures. Nowadays, we have ways of interpreting these, but at in those days, he simply looked at the textures and he said, I know that I have crystals there because I have seen them, right? And of course, there are various different textures. There was this one here, which we now call the Sluckin texture, with or without a small s, Professor. And here are various kinds of focal conic textures. And of course, you will see beautiful, beautiful textures in the week to come. And there are actually books which have nothing but textures which you can buy. Okay. Whenever you have somebody with some new ideas, there's somebody else who says, that fellow must be a fool. And here is the fellow who said, Lehmann must be a fool, right? And so, in fact, he wrote a whole load of articles on liquid crystals, and they were, to begin with, they were entitled On the So-Called Liquid Crystals. And my German isn't terribly good, and I said, look, is this really ironic? I mean, are you sure? But yes, it was really ironic. So there was this intense controversy. There were papers going to and fro, right? He said liquid crystals are cloudy for the same reason that milk is. Would anybody like to drink this liquid crystal? They've been providing us. They provide us with free liquid crystal for our coffee upstairs. Okay, so in fact he's very famous now because he's the founder of modern metallurgy, and he came from Estonia. Actually, of course, it wasn't called Estonia. There were a whole load of Baltic Germans, and he was one of them. And okay, so so there was a big argument in the literature, as always when you have a new phenomenon. Right, there were 2 or even 3 melting points. There was a cloudy phase that was kind of birefringent. There were structural and flow properties which were something between solids and liquids. And obviously, it must be a liquid crystal. But other people said, this cannot be true. And these guys said, no, probably what's happened is that your system is impure. And if your system is impure, and the light scatters, right? That's what you've got in here. You've got little droplets of fat sitting inside your water. If you've got white paint, you've got little droplets of usually titanium dioxide. So other people said, well, maybe it's a suspension of crystals rather than, right? So some people said it was a liquid in a liquid. Other people said it was a crystal in a liquid. And these guys said, no, it must be a liquid crystal. But then the question is, what is a liquid crystal? And so this controversy continued for several years. And why was he so upset? Well, he was so upset because he believed the lattice theory of solids. But nobody had seen the atoms in a solid. Nobody had scattered anything off the atoms in a solid to show that they must be in a regular pattern, right? And so Lehmann said, but Taman said this is, this obviously must be the case. And so the idea that you have something that has a regular pattern and it also flows must be nonsense. So therefore, Taman said it must be something different. It must be some kind of mixture. And if it was a mixture, it must be possible to separate it. Right? Whereas Lehmann said, no, I've seen the liquid crystals. You saw them as well, right? And so he said, this guy is prejudiced. He said, this guy believes the lattice theory of solids. But who knows? Maybe it's true, maybe it's false. Nobody's ever seen these things. But I have seen my liquid crystals. And he was also offended because Taman said, right, you got it wrong. Your observations are not what you think they are. Right? So he was angry that his experimental skill was being criticized, and that's understandable. Okay, so this guy is a kind of acolyte of Lehmann, and so eventually there was a big congress, the German Physical Chemistry Society, the Bunsen Society in Karlsruhe, and so they had a big session. Well, they had a session on liquid crystals. This is Karlsruhe. Well, this is Karlsruhe. Actually, on the Sunday, because just like we had a walk to Grantchester, right? This was 1905. They were going to have a walk to the castle in Baden-Baden. Well, they were if the weather was going to be nice, but the Electrophysical Journal doesn't tell us whether the weather was nice or not, so we don't know whether they went on the walk or whether they did whatever the alternative stuff was. Okay, but the substance of the scientific argument was that, what was it called? Whoops! Oh, I see. It goes back. Okay. Okay, all right. Well, okay. So the substance of the argument was that there was no miscibility gap. If it was a mixture and you had a melting transition, you should get a miscibility gap, right? And there was a discontinuity in the density. So anyway, there was various technical reasons for believing that this cannot possibly be a mixture, right? And in addition, because they hated each other, but they didn't hate each other quite so much, because they knew each of them knew that they were right. So they were prepared to exchange samples, right? I have worked with Hertemann's materials. He says they are not pure. He is right, but they can be purified. And when purified, the liquid crystal phenomenon remains. Okay, he was upset. Taman was upset. There are ruder words than that. He jumps up at the end of the lecture. He goes on and on and on and on. Has birefringence in these cloudy liquids been conclusively established? I am happy to concede flowing crystals, but not liquid crystals. The chairman was a fellow called Van 't Hoff. He was a very famous Dutch physical chemist. He was the first winner of the Nobel Prize in Chemistry. He had moved from Amsterdam to Berlin because they offered him less teaching. Can't imagine why. Anyway, right. And obviously, they had these guys who were going to kill each other. And so obviously what you have to do, and it was also lunchtime, I should say. And probably it was lunchtime rather than the fact that they were going to kill each other. So anyway, so this is the report that's in the right. Proposed the formation of a committee of experts who would examine the liquid crystal further, and the committee would include blah, 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 blah. And the war went on, and now we get a question. We get a question, right? Are liquid crystals a type of dishwashing liquid which look crystalline when you blow? Whoops! Yay! A magic type of gooey crystal which will give you good luck. If you look them up on the web, you will know that that one is right. Neither liquid nor crystal, but something altogether different and more interesting. A material with some liquid or some crystalline properties. Now I'm going to press the button now. Everybody vote. We've gained more people, or some people are voting twice. Oh no, you're not allowed to vote twice, right? Right. Can I?
No, it's still going up. The number's still increasing.
Right, well, you know, this is like one of my Monte Carlo simulations, and we want to know whether we've achieved equilibrium, and the answer is we never have. Okay, now what? Do I press this button? Okay, they are neither liquid nor crystal, or something altogether more interesting. I guess that's probably the right answer, but I suppose you could say that D was the right answer as well. And incidentally, C is a quote, and it's a quote that we shall see in a moment. Hang on. Oh, I need to press something, don't I?
Yes, Control L.
Pardon?
Control L.
Control L.
Anywhere on the screen.
Anywhere on, sorry?
On the screen.
Okay, this is a great poster. This is Merck, of course, you will have heard of, right? And Lehmann developed a close relationship with Merck, right? The Merck company is the oldest chemical company in Germany. It's privately owned. You can't go and buy shares in it. And it's still making liquid crystals. It's still the leading producer of industrial liquid crystals. And they were on the lookout for something that might be interesting, even though a whole load of, of Lehmann's colleagues said that this is, not to find a point on it, a load of crap. And this is great, isn't it? It looks like a kind of advertisement for some kind of theatre, you know, where there's going to be some kind of music hall kind of performance. Okay, so I should say that there was a lot of controversy between Lehmann and the chemist Daniel Vorländer, whom we're going to hear about, controversy between Lehmann and Reinitzer, controversy between Georges Fidel, who's a French guy that we're going to come up against in a minute, and Lehmann. They all hated each other. And the only ones that didn't hate each other was this fellow Haeckel. And Haeckel invented the idea of ecology, right? So if you want to know, and Haeckel was trying to...
Tim, your microphone has gone off again. If it's being recorded, please.
Oh dear. Does it work now?
No. Press the button.
Press the button.
On button.
This button. Yay. Thank you.
Yeah.
Thank you.
Mute switch or something?
Okay. Is it red? Can you hear me now?
Yeah, it's fine. We can hear you without.
Red's bad. It's changing. What am I doing to these batteries?
Overloading them.
Okay. All right. Okay, here's another interesting guy. You can see how interesting he is. He's actually the first chemist who really, his lab started in Halle, actually. His lab started making stuff. And he discovered that liquid crystal molecules looked like rods. And the chemistry is a bit too complicated to explain why, but here are various different kinds of liquid crystal molecule. This is my favorite liquid crystal molecule, which is like a piece of chalk, and these other ones are kind of fake chemical kind of molecules, and which apparently, well, I mean, who knows? Anyway, so right, and the thing was, he wrote a book. He wrote a book. Actually, the book was in German, I suppose. You know, the sentences were only like 40 words long instead of 213. And so Lehmann, right, and so when he wrote the book, he said, well, it's not clear quite who discovered this. Maybe it was discovered by Lehmann, and maybe it was discovered by Reinitzer. And so Lehmann got very upset indeed. In a book published recently, The Origin, it was described, one might suspect from this book, that this other guy had actually discovered the phenomenon, and I had merely renamed it. I present for the first time the full story. Okay, so as a result, we get a quiz, right? Who was the real discoverer? Was the real discoverer, we haven't come across this Virchow person yet, but we will, because in retrospect, he was the first to observe them. Was it Reinitzer, because we can trace liquid crystal science back to a paper by him? Was it Lehmann, because he was the first to realize that they were a special phase and do some investigations? Was it, all right, let's press the button. Right, was it Gattermann, because he was the first to synthesize a liquid crystal in the lab? Or was it Friedel? We'll come across him as well. He was French because he was the first to understand liquid crystal structures. Vote now. We are voting. We are voting. And you need to be ready, Ivan, because I'm going to break the machine again. Can we stop? Oh no, what's happened? Do I need to start all over again? Oh dear. Does everybody have to vote again, or is it? Oh, this experiment business, it's so hard. Okay. All right, everybody who hasn't voted, vote now. Okay, never mind. Right, now I press this. It was? What's happened? It's, pardon? Okay. So Lehmann wins, right? But you can see that this is like Who Wants to Be a Millionaire? You know, when you go, Who Wants to Be a Millionaire? And they ask the audience, and the audience can't make up their minds, and the person is completely flummoxed. You know, they like it when 93% of people are voting for one guy, but in this case, right, those who say Lehmann are probably with the majority, but only probably with the majority. And now, what am I going to do? All right, now what do I do? Press the screen. Okay, that's cool. Margarita, you use these? Okay, so look, there was a lot of discussion, you know. Lehmann said that liquid crystals were things that were like alive, and here we have some pictures that show he went back into the literature. He discovered that there was a physiologist in the 1850s who had observed nerve fibers in water, and it turned out that these things were birefringent. Here's a picture in which he was showing these are the kind of so-called myelin structures, right? So Lehmann made a big deal about the possibility that liquid crystals were associated with life because they had certain of the properties that living objects had. And he was too early. But the basic program that said, can you reduce physiology to physical chemistry, that's probably not a bad program. But of course, big surprise, he got into a big row with the professor of theology. Can't imagine why. This is another interesting thing. I have been asked if the crystalline liquid, Forlander always talked about crystalline liquids, not about liquid crystals. Substances may be technically exploited. This was in 1924. I do not see any such possibility. I expect he was on a big consultancy fee. Okay. The theorists had a go, and they didn't do terribly well. So there we are. That's the theorists. At some point, work started in France, and I'm running out of time, so I'm going to do this a little bit quickly. But there were some French groups that started working on these things. This is Georges Friedel, and this paper, called The Mesomorphic States of Matter, written in 1922. It was actually his thèse d'état. It was kind of a Doctor of Science thesis, because he had been transferred from the civil service to the university, because after the First World War, the French reconquered Alsace. And when they reconquered Alsace, Strasbourg became French again, and you obviously needed some professors, but he didn't have the right degrees, so this is the thesis that he wrote, and probably it's the most cited article in liquid crystals, right? They published several papers early. You see here are the kind of things that you would see under a cross polarizers. You'd see these patterns. We are still seeing these patterns. They were called, I guess, liquids with centers in them, and these were the liquids with strings, and they were drawing some distinction. Of course, it could have been that these guys and these guys in some sense were different. Now we know that these are just different manifestations of the same thing. And what he said was, look, on a larger scale, the collection of, this is what the individual drop looks like. If you have a whole load of them, then they look cloudy, and that's why the liquid crystal here is looking cloudy. Okay, so Friedel really transformed the subject. He introduced the modern terminology, smectic, nematic, cholesteric, although you must never call it a cholesteric nowadays, because they will tell you to call it an N star. Right, he identified the liquid crystals as distinct new phases. He didn't like the terminology liquid crystals, because now he understood that they were not liquid crystals. He tried to call them the mesomorphic phases. He realized that structure and not degree of fluidity was the important property. He described qualitatively the main structural features, the optics, and so on. So now, in some sense, it became science. Here is and I should say, for those who can read the original, you should read the original not just for the science, but also because it is a beautiful piece of literature. And if you want a translation of that beautiful piece of literature into a piece of beautiful English, you could do worse than read my translation in my book. Okay, so he was known for his strong opinions and acerbic style. Here he is, here, right? Lehmann had the great merit of drawing attention to these substances, but he named them wrongly. It's poor terminology. And here we are, you see, something infinitely more interesting than would be the case, right? Than if they were simple crystals exhibiting some unexpected degree of fluidity. So that was in one of the answers to one of the previous, right? And here's something else, right? Friedel came from Strasbourg, and he had a house. The Friedel family had a house in Alsace, and the Germans took it over, and he was upset. He was seriously upset with the Germans, but of course, it was nothing to do with the fact that he was expelled and they took over his house. No, Perisher thought it was nothing to do like that at all, right? The German authors seemed to be little concerned. Lehmann, well, it was okay. The rest of them are confused and rendered still more unclear by the theoretical considerations which accompany them. It has been in France above all. Well, of course, who can argue? Who can argue? So that's the next question that I have for you. Right, now what do I do here? I press the button. Friedel was right. Germans really are stupid. Friedel was wrong. Germans are really very smart and should be given credit for discovering liquid crystals. The boring answer, scientists are human and carry the same prejudice as other humans. Right. The autistic answer, these questions are not of interest to us. We are here to do science, are we not? And not sociology. And E, I know there must be a Korean or two in the house. Both Germans and French are equally stupid, and actually it's Koreans who are smarter than everybody else, and that is why modern display devices are exclusively made by Samsung, and we have only 31, 33, 34, I'm waiting. Well, you want to come and help? 43. Right, have we converged? Are we done? Right. The one person who says that Friedel was right, Germans are stupid, may wish to hide, I guess. Whoops. All right, and another question, because I know you like answering questions, right? And I have to tell you, they're all blokes. I know, this is right. I'm sorry, but in those days there were very few women in science. The first occurrence of women in liquid crystal science actually comes in the 1920s. There was a Dutch lady called, who worked with Ornstein and is referred to as Miss Rivkin. Okay, so you have a choice. Who was the best looking liquid crystal pioneer? Was it Lehmann, Schenk? There we are. All right, was it Lehmann, Schenk, Taman, Forlander, or Friedel? We've converged. Somebody thinks they're all ugly. Sorry, I only had E. I wouldn't have, none of the above. You have to, sometimes when you do questionnaires, you have to force people to make a decision. Right, there's 2 people who haven't voted. Come on, everybody, vote. You're going to lose marks if you don't, but thank you. Okay, now I'm going to tell you something interesting. He was a Nazi. He actually belonged to the Nazi Party. This guy here, he got the Iron Cross from Hitler, wore it very proudly. This guy volunteered in the Second World War despite having retired, but unfortunately was struck down by cancer, and his obituary, which was written by a well-known Nazi, somebody who actually wrote essays about German chemistry, we've seen what a moderate sort of fellow Friedel is, so they're all really nice people, right? All really nice people, but of course it has no effect, no relevance to their beauty, right? Whoops. Here we are. All right, let's see how the vote. Do I need to press this? Okay, let's see what. Okay. All right, we like Lehman, we almost like Taman. Nobody like. Not really surprised that I have to say that I'm not really surprised that nobody likes Vorländer. I mean, whoops. I mean, you really, if you met a guy like this on a dark night, you'd be a bit concerned. But his chemistry was great, and not only was his chemistry great, regardless of his political views, and regardless of the fact that he was, how can I say, aesthetically challenged, and regardless of the fact that he had forgotten to shave on the day that our photographer went to take a photograph, his chemicals survived. His chemicals survived out of good luck. His chemicals survived because the local. They were in the way of the American army at the end of the Second World War, and some local commander made a deal with the Americans, and so the Americans didn't bomb Halle, and so almost everything in Germany was bombed towards the end of the Second World War, and to this day, Vorländer's chemicals are sitting in a cigar box in Halle. Okay, so let's. There we are. And now, okay, so we, all right, this guy is Russian, and he is the Fredericks of the Fredericks effect, and this is the Fredericks effect. The idea is that if you put liquid crystals in a thin sample, you need a critical voltage, right? And actually, this is a particularly interesting effect, because it was this effect that brought the elasticity theory, which everybody learns. Everybody calls the Frank elasticity, but it's not the Frank elasticity, it's Ozen's elasticity, and it was Zocher who did the calculation, and previously there was an entirely different theory. People said, constants, elastic constants, how can you measure the elastic constants? And eventually there was a prediction that said the Fredericks effect allows you to measure the elastic constant. Okay, I'm going to try and do things a little bit more quickly. I'm going to just move on to some more modern stuff because, right, we all know, we are all interested because my screen here is a liquid crystal screen, and of course that's why if you talk to people at a party and you say, I am in liquid crystals, they say, oh yeah, that's right, and then they tell you about their plasma screen, of course. But okay, so the first patent was granted in 1933. The first patent for a thermochromic thermometer, the one that you use for your children or your lecturers when they're getting too hot, that kind of stuff. So that dates from 1960, from the Westinghouse Corporation. Here is the patent, actually. There's the patent. It was from Marconi. It was British, from the days that we used to make things in Britain. Nowadays, well, what can you say? Of course, Marconi, now Marconi, it's a really old English name, isn't it? Everybody can tell that. And actually, the interesting thing, of course, was that Marconi came from Italy precisely because England was the place to do scientific and to make industrial work, and eventually went back to Italy in the 1930s because Mussolini was just such a great guy. And they were trying to make TVs, right? And so these guys had the idea was, how could you turn electric currents into pictures? My engineering friends tell me this machine would have blown up. It wouldn't have worked. But anyway, it was interrupted by the war. I tried to discover about this guy. This is the actually Nyman Levin I tried to discover. He later became the head of the British Atomic Weapons Research Establishment, and all record of him has been removed entirely from the press. You can't discover anything about him. The only extant obituary is in the Jewish Chronicle. And even then it doesn't say anything about him. It just says that his wife was active in the synagogue. Okay, here's a picture of Ferguson and the thermochromic thermometers. There it is. You see lots of different pictures, colors, and the colors change depending on the temperature. And it's because the pitch, right, as things get warmer, the pitch of the cholesteric changes. Right. So the key work for modern display devices was done really in the 60s and early 70s, and you won't find much in this story about the Japanese and the Koreans, because that's the interesting thing. The basic scientific work, at least for screen devices, was done in Britain and in the United States. But actually, making the devices, the exploitation, worked in the Far East, and it's an interesting question as to what were the social factors that allowed all of this to occur. Right, 1988 was the first small flat screen. Those of us that were around then remember these things. Actually, before then, there were these watches. What happened was that Sharp made some watches. They made some watches, and it turned out that somebody took them to Hokkaido. It was winter time. They stopped working. Right, everything had to be withdrawn, and that's why you need to have such a wide temperature range. Here is a picture of light transmission through cross polarizers. Here's another picture of the Schlieren texture. And here is, right, so the twisted pneumatic cell, which is due to Schacht and Helfrich in 1970. And again, it's all to do with this critical field, critical voltage that you need. And so depending on whether the field is on or off, things look black or transparent. And no doubt we will discuss all of this. Here's a picture of how these things work. You can see that when you put the voltage on, right, there's the molecules line up with respect to the voltage. The polarization doesn't change. When, on the other hand, the voltage is off, then the director twists around, and as it twists around, the polarization twists around, so things can get through here, and they don't get through here. And so that's the basic physics of how all of these things work. Here are some pictures, much younger pictures of some of the key players. Right, this fellow Hallmeyer was the driving engineer at RCA, Radio Corporation of America. Why? Right, so RCA had labs. They had labs that made things. They were investigating TVs. They discovered things that you could make better screens. What did they do? They suppressed the information. Right, we have a monopoly now, and now we won't make such big profits. It's a bad thing. And so it was competing companies that, right, it was impossible to persuade managers that this was a good thing to do. This fellow had the idea of twisted pneumatics while working at RCA in New Jersey. He went to see his boss. The boss said, "I'm not interested." He went back to Europe, teamed up with this guy, worked with a chemical company, Hoffman La Roche, and the rest is sort of history. I have to mention George Gray because he was the Scottish chemist who actually made this molecule and molecules that are like this, that enabled the liquid crystals to work at room temperatures, and only if you could get liquid crystals to work at room temperatures could you have a device. And so that was something that, right. Here is Ferguson, right, who constructed a twisted pneumatic device. Big controversy, patent wars all over the world between this guy here and the European group. I never got a chance to talk to this guy, but I wouldn't want to repeat what the European group had to say about him. But you have to believe in your product. This guy here, Leslie, he made the theories. You can't commit enormous amounts of money to make devices unless you've got something that works, right? Something that you can predict. So there are other kinds of devices that we regularly work on. We know that they work, but we don't know what will happen if we change the parameters, and so industry is unprepared to spend millions on a production line. Right? His theory, incidentally, was to do with a magnetic field. That he had no idea at all when he made a theory of these things that he was making a theory for a newly emergent screen technology. Okay, so I just wanted to make the point in this slide that even when you are making liquid crystal devices, right, engineering is absolutely key, because there are a whole load of things that have nothing to do with liquid crystals at all. And there are a whole load, no. Oh, there, we're back again. No. There we are. Okay. So you can see that to get the technology, you have to ask all sorts of questions that that a mathematician or a physicist would never ask them. Refreshing, how quickly can I switch it, right? How do I get the colors to work? Dither means changing things, but is it because my eye integrates over space or time? And everybody who has a liquid crystal screen will know that if they go to the wrong angle, they can't see it. I mean, it goes black. It's not just that you can't see it because you're on the wrong side. It's gone black because you're at the wrong angle. So there's that, right? So don't knock the engineers. Can I have my fee, please? Okay, here's a nice big Japanese television. That was before the Koreans started to take over. And this is a picture that one of your colleagues sent. Well, maybe it was you. Sent to me from Colorado, showing that you can have very big screens or very little screens. Okay, so we're nearly done. Right, big question. Why could the US and Europe do the science but not do the engineering? Well, one Japanese guy, he worked for IBM, so he must know, right, it was a suitable technology for the Japanese mentality. I don't think, again, it's not terribly politically correct. It's not something that would want nowadays to be quoted saying, but it seems more likely to have something. Mentality, I suppose, is another word for cultural factors, right, which one can't quite put one's finger on, and it's certainly at least more likely to be that than racial factors. And of course, as I've mentioned previously, the US had prior investments that needed defending. You're less likely to be adventurous if you are the market leader. You're less likely to think that these other guys are going to change the game entirely. All right. Here's a picture just showing how liquid crystal screens took over the market. This is slightly old, but you can see that in 2000 it was worth 20 billion. Now it's worth much more than that, and you can see how liquid crystals took over the market between about 1987 and 2000. And now I have a question for you, and then we are almost done. Right. And it's to do with you as a citizen rather than you as a scientist, right? So just look at the various different options. Right, the government should fund basic liquid crystal research because science is an important part of culture, right? Oh, but governments should fund liquid crystal research because historically liquid crystals have turned out to be useful. Or governments should fund liquid crystal research because liquid crystals are at the heart of understanding life and implicitly will help you cure cancer, right? Bound to get lots of money for that. What about industrial companies? They should fund liquid crystal research only if it can see a short-term application, or industrial companies should fund liquid crystal research because liquid crystals have such a good applications track record. Vote now. Few people haven't voted. Oh, no, they have now. Oh no, they're still. Well, oh, I see. I didn't hit. Do I need to hit stop first? Yeah. What's? I think we're going to stop. Okay. It did look as though people started off with the idea that they should fund fundamental science because science is an important part of culture. But you try that argument on, right? When you just try going down to the pub, actually. Try it at the Eagle tonight, for example. Okay. Right. Okay, so here are two people who thought about liquid crystals and actually did get the Nobel Prize, and at least one of them was not interested in industrial applications, and the other one was vaguely interested in industrial applications, but not while thinking about liquid crystals. And let's, whoops, where are we? Okay. I'm going to miss out all of this because we are more or less out of time. Right, Kevlar. Right. This is my opportunity to wear a helmet. This was made, this is Kevlar. It's a very strong material, and it can be, right, and it was, at least in its liquid form, a liquid crystal. And if we can find a cricketer can attack me with this, and you will see that I survive. And I want to say that's because we are insured at the Newton Centre. Who's a cricketer? Can I find a cricketer just to throw the ball at my head? I mean, yeah, not very hard. I need some other people to make sure that they can catch the ball. I don't think which way it's on is relevant for its scattering properties, how it scatters cricket balls. Why don't we put it on the floor? Shall we? There we are. There we are. Can you? We've tried this. Try this at home. Try this at home, and if it doesn't work, sorry. Okay. All right. I think, okay. My only point in these slides was to say that liquid crystals are important in the phenomena inside a liquid crystal cell. Here are a variety of things that we may have time to talk about for the future of liquid crystals. Here is some more speculations. I do want to say something else about liquid crystals, though, and that is that it is a multidisciplinary subject. And those of us that have been involved in this for some time, one of the most interesting things is that you meet people from different disciplines, and you have a chance to look at the world in a slightly different way. And here, mathematics, computer science, biology, engineering, physics, chemistry, and you've seen those pictures. Those pictures are really quite beautiful, right? Nature has provided us with an exceptionally beautiful subject that is not only beautiful because of what goes on inside our brain, but also because of the way it hits us from the outside. Here are a set of acknowledgements, partly to my co-workers, partly to people whom I have shamelessly plagiarized, partly to people whose books who have written to me, either some of whom who've written to me and subsequently died, some who helped me to understand Lehmann's German and the 230-word long sentences. And finally, okay, your library. If your library doesn't have this book, your library should have this book. This has reprints of all the key papers in liquid crystals together with a commentary. And although you can download this book from a Belarusian and a Chinese website, I guarantee you that it will carry the virus from which your computer will never recover. Right. That I personally put there. Right, anyway, but more to the point, it's coming out in paperback this autumn, and so if you can't afford it at something like 10 quid, then your library should your library should get lots of it, and use it for a philosophy of science course. And that must be the end. Yeah, that's the end. Okay.
So we run just 20 minutes over time.
I'm really sorry.
But while we will assemble our panel, maybe we have 1-2 quick questions. So please, panelists, come to the stage and please help us bring the